Hi, good evening, everyone. I have prepared this schedule for revision for the purpose of IIT JAM. Now, these are the important and difficult topics that I think. If you think that there is something which I am missing and you want me to focus on, I can go ahead and I can add that topic also in this list. Okay. But otherwise, according to me, this is the schedule that I will be following starting today till 29th. 30, 31st, and 1st, we will not be having the session so that you can go ahead and you can revise. And for the rest of the days, this is the session that I will be following. If you have any other topic in mind, you can go ahead and you can let me know, and I will add that to one of the days. Okay. Okay. Let us go ahead and begin with today's session. And I wanted to do some questions first of all today, right? So take this question, try to do this question, try to answer this question. This is based on whatever optimization classes we have done in the past. Okay, B. What about others? Good. So let's try to see. It says for what value of k the function is convex. So you find out the first order condition, f dash x1. It will give you 2 minus k 2x1 f dash x2. This will give you 2x2. Find out double derivative with respect to x1. It will give you 2 minus k. Double order derivative with respect to x2. It will give you 2. Formulate the Hessian matrix. Here you will have 4 minus 2k. Here you will have 2. If you differentiate this with respect to x1, it will give you 0. Right? For convexity, we need positive definite, right? So we need that this should be greater than 0. So 4 should be greater than 2k. So k should be less than 2. And we also need that the second principal minor should also be greater than 0. So this into this minus this into this should be 0. So 2. 4 minus 2k minus 0 should be greater than 0. 2, 4 minus 2k should be greater than 0. 4 minus 2k greater than 0. Same condition. So k less than 2 is the right answer, which means that the correct answer will be B. The correct answer will be B. That is the correct answer. Good. Okay. Go ahead, take the next question. Try to do this question yourself now. For what value of k, let me just read it out. For what value of k, function fx is positive semi-definite? Give it a try. Okay, C. How about others? A, C. Okay, let's see. So for positive semi-definite, what, what do we want? First of all, let's find out the first order condition. So f dash 1 will be 2x1 into k minus kx2. And again, if I differentiate this with respect to 1, I will get, with respect to x1, I will get 2k minus 0. So I'll get 2k. Differentiate this with respect to x2. You will get 2x2 minus kx1. And differentiate this again with respect to x2, you will get 2. Differentiate this one with respect to x2, you will get minus k, right? So what is going to be your Hessian matrix? 2k, minus k, minus k and 2. All of us are getting this as the Hessian matrix. This is going to be the Hessian matrix. Now, positive semi-definite says that I need my leading principal diagonals to be greater than equal to 0, but my first leading principal diagonal, keep in mind, my first leading principal minor should be strictly greater than 0. My first leading principal diagonal should be strictly greater than 0, which means I need that this 2k should be strictly greater than 0. And I need that this minus this can be greater than equal to 0. Right? So 4k minus k square can be greater than equal to 0. So if I take k common, 4 minus k can be greater than equal to 0. Now, when will this be 0? Under two conditions. Either when k is 0 or when k is 4. But I need my k to be strictly greater than 0. I need my k to be strictly greater than 0. So the only answer I'm left up with is k equal to 4. So the correct answer will be C. That is the correct answer. K equal to 4 will be the right answer. Is this clear? Isn't F1 to 0? How? This is my differentiation with respect to x2. Now, if I differentiate this with respect to x1 now, so I have x1 here, so it will be minus k. And this is my differentiation with respect to x1. So if I differentiate this with respect to x2 now, it will be again minus k. Right? It will be minus k. Last part. So we need positive semi-definite. Now, positive semi-definite says that we need all leading principal diagonals to be greater than or equal to 0. But my first leading principal diagonal should be strictly greater than 0. Right? So I need that my first leading principal diagonal, that means this, it should be strictly greater than 0. So k needs to be strictly greater than 0. But I also need that my second leading principal minor, which will be this minus this, it can be greater than or equal to 0. So I have 4k minus k square greater than equal to 0. Okay. Now, when will this be equal to 0? Under two conditions. Either when k is 0 or when k is going to be 4. But k cannot be 0. I have already said k should be strictly greater than 0. So this is eliminated. It means that k should be 4. When k is 4, my second leading principal diagonal will become 0. But it will still be positive semi-definite. The condition of positive semi-definite will still be satisfied. Right? So that means that I can have k equal to 4, which will satisfy both the conditions. Is this clear now? Can you tell me what will be condition for positive definite? What will be the condition for positive definite? Just find that out now. K greater than. Yes, that is correct. So for positive definite, I require that k into 4 minus k should be strictly greater than 0. Beta, use inequality. Use inequality. When is the product of two things strictly positive? When both of them are positive or when both of them are negative. तभी तो प्रोडक्ट पॉजिटिव होगा. सो k greater than 0 and 4 greater than k. It means that k has to be greater than 0 and less than 4. This gives me k between 0 to 4. And this is k less than 0 and 4 less than k. Right? So k less than 0 and k less than 4. Isn't it? Isn't it? So it means that you will go ahead and you will get two conditions. Right? Sorry, k greater than 4. This one. K greater than 4. So there is no common here. Right? Nothing is common. So that is correct. That you will get only one. Whenever k will be between 0 to 4, you will have your answer as positive definite. Now in exam, you can also get a question which is a little different. जरूरी नहीं है वो पूछे positive definite. They could have asked you that for what value of k will this be a concave function or a convex function, right? So then again you have to do वही चीजें, positive definite or semi definite, but you have to just think differently. That is the only change that you will be going ahead and you will be seeing here. Otherwise the question is going to be the same. Okay, give this a try. There is a function from r square to r square. The function is this. You need to tell me what will be the saddle point of this function. Function is x square 2 minus y cube plus 3y square plus 9y. Tell me the saddle point of the function. Anyone? Just do it by elimination otherwise. Okay, 3, 2 minus 3, 2. A, B, fine. Let's see. So we need to find the saddle point of the function. So first of all, what we can go ahead and do is, let's find out the first order condition with respect to x. 2x, 2 minus y, and that's it, right? Second order derivative, 2, 2 minus y. First order derivative with respect to y, x square minus 1 minus 3y square plus 6y plus 9. And second order derivative with respect to y will be minus 6y plus 6. And f double dash xy will be 2x minus 1 minus 2x. Formulate the Hessian matrix. Just go ahead and formulate the Hessian matrix. So what will you get? 4 minus 2y, fxx. I've written here. Fyy minus 6y plus 6. Keep checking the calculations. Fxy minus 2x minus 2x. First condition for saddle point is that whenever you see this becoming 0, that is where you will know that it's a saddle point. So 4 equal to 2y, y equal to 2. That is your first hint towards the saddle point, that this first leading principal minor is 0, right? So from there only you can start eliminating. Now the second hint for this is that we have always seen that the second leading principal minor should be positive. If it is negative, it's a saddle point. So let's find the determinant. 4 minus 2y into minus 6y plus 6 minus 4x square equal to 0. So, less than 0. I want this to be negative. Whichever point satisfies this condition will be your saddle point. Whichever point satisfies the condition that when you find out the determinant, the second order Hessian leading principal minor, that means this minus this determinant. If it is negative, then definitely it is a saddle point. Okay. Now I've already found out that my y is 2. I've already gone till some level. So I can just put y as 2 everywhere. So I'll get 4 minus 4 minus 6 into 4 into 2 plus 6 minus 4x square less than 0. Right? Just find out which x satisfies this condition. Whichever x will satisfy this condition, that x will be your saddle point. Whichever x satisfies this condition will be your saddle point. So I think that in our case, both these x's will satisfy this condition. 3, 2 also and minus 3, 2 also. Both of them are satisfying this condition. So both of them are apt for the saddle point. So answer will be both C and D. Both are correct. C and D. That's the answer to this question. Right? Okay. Try this one.